All right. Hello, audio hackers out there. This is Sega Sonic Fan, and today I want to show a really easy way to hack almost any sound system to remove ground hum. Ground hum, of course, is very annoying, and nobody likes it. Today I was doing this with a Boston Acoustics MM220. This is a two-channel. Actually, it's more than two channels. No, I take that back. I think it's just two channels, and but it's more than two drivers. It's a stereo speaker set that was made for PCs. Just a quick look at it. I really like it, and I use it for my bedside gaming setup, and they're very affordable. Here is one of the speakers. If you take off the cover, though, looks kind of standard. But if you take off the cover, you'll notice it's got a passive woofer, two drivers, and a tweeter. It's pretty snazzy, and it sounds nice. Minus the friggin' ground hum, which really sucks. And I just got Cotton Reboot in the mail, as some of you familiar with my videos are probably aware. And the hum was like really annoying me and taking away from my experience of my new game. So I wanted to fix it. I'm going to show you how. This hum, by the way, is also common to KRK sound systems and pretty much anything designed in a similar fashion. First, a quick explanation of how ground hum is created, what causes it. It's usually when there is audible feedback, so frequency feedback through the actual AC wires into your other device. So essentially, your two devices are sharing current through your AC outlet, which is why you can also get rid of hum if you hook up the two devices to a different part of your circuit breaker. Like say you run an extension cable to another room, you can get rid of hum that way. That's a really annoying way, but it's possible. The other way you can do it, which is expensive and also kind of annoying, is you could get a large isolation transformer. They're like these big bricks that are transformers in and of themselves that isolate the electrical current, similar to, if you ran wires to a different circuit. So those are ways you can get rid of ground hum, but they're not ideal, and one of them is quite expensive. The other way, there is another way, is to either sort of quote-unquote repair the hum, which is what a lot of people do with KRKs. A lot of times the hum is caused by a large capacitor aging and not cleaning up the power supply noise, not doing what's called ripple rejection and frequency rejection as well as it used to when it was brand new. And given that this power supply, for example, is huge and it's a very large value, it's a 4700 microfarad at 35 volts, which is substantial. This capacitor probably cost close to as much as the entire audio chip amp, possibly even more. Though probably not for an amp that size, but still, for manufacturers, that was probably a $3 part or something, which is substantial for a budget sound system, especially, and even for a KRK. So a lot of guides online will just say, well, replace that capacitor and things get better. And it's true. Many instances that does help a lot. But in the course with my KRKs, it did not solve the problem. I ended up actually getting an isolation transformer it cleaned it up a little bit, but there was still some hum there. Because it's a failure in the design of the system. Ultimately. Like you can kind of make things a little bit better by changing capacitors, but it's ultimately a design failure. And the difference is, the reason it's caused is because it's using a class 1 power supply. All these systems generally use a class 1 power supply, which is this big brick here. And I guess these are better for audio because I see them a lot in audio. And it's not a switching power supply. So a switching power supply uses pulse width modulation to switch at a certain frequency the alternating current and the direct current as well. Actually, I think it's direct current that it switches the direct current. But it uses an opto-isolator, and an opto-isolator is a special little, I don't have one in front of me, but it's a little black box, looks like a little chip, usually got 4 pins. 2 of them are a diode, a light-emitting diode, and one of them is an infrared, usually infrared diode, and a photo optocoupler. And so what it does is it actually switches the power supply, it switches the AC and DC visually. That's why it's called an optocoupler, because it's opticals. It's using optics. They're super cool, and they're used to isolate power supplies, and they're used in all sorts of modern power supplies like this, which is why modern power supplies, if they're made well, don't have that problem. And why aren't all power supplies just doing that and have optocouplers? Well, one is cost. I think it's probably cheaper to just get something like this sometimes. And two is, I think some manufacturers, I don't know the details of it, feel free to comment if you do, but there are some audio advantages to not using a switching power supply. I've never noticed it myself because usually the switching frequency is the only problem, and that frequency is usually outside of the range of human hearing, like 200 kilohertz or more, or 20 it's usually well above 20 kilohertz, which is the maximum range of human hearing usually. And yeah, I mean, I haven't normally experienced any problems with that, so I'm guessing it's mostly to do with cost, but if anyone knows, feel free to post here. Regardless, there are things you can do beyond just changing a capacitor, which ultimately doesn't really permanently fix the problem. So first off, I thought I was going to be clever and put in this switching power supply. And so what I did was I went and looked at the circuit, and it's very straightforward. When you see these big transformers, the AC voltage comes in here, and then you have 4 diodes, large diodes, that form a bridge rectifier. If you don't know what a bridge rectifier is, I suggest looking it up. They're super useful to know about, and they're used almost always in converting AC to DC voltage. And it's just 4 diodes, really simple. They have to be large diodes like this because they're switching a lot of current, because this is an amplifier. But they can be quite small as well. There is a fuse here, as you can see. And what's weird about this is I actually originally thought, well, you're just going to use these 4 diodes, and then there's always a large capacitor at the end to clean up the ripple. And so you got the 4 diodes, you got the large capacitor. All I got to do is just plug in the voltage where the capacitor is and disconnect the diodes, and I should be good to go and plug in my own power supply. I measured it, and it turns out it's around 20 volts, which makes sense. By the way, if you're curious and you're kind of questioning what voltage what it might be, you can start by looking at the rating on that capacitor. This capacitor is rated at 35 volts. So I was like, this is going to be probably 20 to 25 volts. And it was 20 volts. So I found a 20 volt power supply. You can get them from any old laptop or whatever. And thought I'd inject it and, just solder it in right there where the capacitor is and take out the diodes. And I thought I was really clever and, solved the problem. But I did not. Because when these kind of systems are used, when the AC voltage comes in, sometimes they will also create a second voltage for the other parts of the circuit. And in the case of this, it definitely does that. There's this fuse, and you have this diode going over here. And if we zoom in, let's see if we can zoom in more. Try to focus a little bit too. Oh, come on. Focus, camera. Be nice. Cover the lens, see if it'll focus. Oh, there we go. So if we look at this circuit, our AC voltage comes in here, and there's this fuse here, which then goes to our big diode array, but there's also this diode which goes over here and then goes to this circuit and goes to some other stuff. So when I plugged in my 20 volts, it didn't turn on because there's more to the circuit than that. And I kind of looked at the parts, and usually the way you can try to find out where that other voltage is generated is to find another bridge rectifier on the board. And I had a hard time finding one, to be honest. I don't know I honestly don't know where it is or what that other voltage is doing. And I'm looking at it now, and I'm still not seeing any kind of bridge rectifier. Maybe this chip in the back is a diode and helps out with that. Maybe, I don't know. I don't know what they're doing with the AC voltage, the secondary voltage there, and I didn't really care enough to spend a bunch of time on it because, like I said, it's just a cheap system to get some hum. I just want to get some hum removed. I'm not trying to spend 2 days working on this. So I said, screw it. Not gonna use an external power supply. I'm gonna use the same one that it comes with, and we're gonna solve this hum another way. The original way, I should have done it probably, but I thought I was being clever. And the original way that I thought of, which I wanted to share with you, to wrap everything up. If you watch this video, this is the part you're probably most interested in. the quick and easy way to get rid of hum, and sorry I gave some background there, but sometimes that helps some folks, is you just add two diodes. Two diodes. You make them large current if you're using a large current source like this. And you get one that'll pass the ground. You find where the DC voltage ends up, which is the end of that bridge rectifier, which is essentially where this capacitor is. However, there's two traces that ran to that capacitor. One is here, which is the minus, and here, which is the plus. So there's 4 diodes. They create minus, plus 20 volts. So what I did was I took my Dremel, I drilled in here and isolated the circuit. So I isolated that capacitor from the input. From the output voltage of the bridge rectifier. You isolate it, so there's no connection there, and then you put 2 diodes, one for positive, one for minus. And of course, you flip the anode and the cathode for the negative. Why does this help? Why does this help? Well, diodes, by their very nature, allow current to only flow in one direction. So this is basically working as a really janky sort of optocoupler, because it's saying you can only let current go that way for the ground and the positive rail. Nothing's going to go back, which means this will not share current with your other devices using your AC outlet. Now, in technical terms, practically speaking, yes. There is a tiny bit of leakage current across diodes. You don't get that with an optocoupler. That leakage current is infinitesimal usually, especially if you're using a nice Schottky diode. Very, 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 very small amount of current. It's usually in the couple milliamps or less, so it's pretty negligible. So essentially, this is going to function as a one-directional current regulator, or I don't know if I call it current regulator, but a directional current circuit, and we'll stop the hum. Now, I'm going to use a device that I'm going to use 2 audio inputs to give you a sort of an example of what the hum sounds like, and then I'm going to play you a song and you'll hear it with this new fix. Now, safety precautions, if you're doing anything like this, wear gloves, especially with high voltages. 20 volts can definitely hurt. It's not going to kill you, but it's going to hurt. And if you don't, make sure you're using an isolated workspace, electrically isolated workspace. In this case, I didn't want to leave it on my carpet, so I got I got a Quincy Jones record here. It's the next best thing, right? So Quincy Jones is keeping our circuit safe. His birthday just happened, I think, by the way. Good old Quincy. And so yeah, everything's electrically isolated. I'm wearing gloves. The one thing this circuit is missing is a fuse, which I'm not thrilled about. You can see here the AC lines just go right in. There's no fuse. So I might add that later, even if I haven't had problems with this. That is a big design flaw. Really never should do that. Fuses are, not as cheap as you might think. They're actually one of the more expensive passive components. So manufacturers like to cheap out on them, which is unfortunate. Okay, so I'm going to plug everything in. Well, first I got to plug in the actual transformer here. And I want to make sure this part is not coming up. So this goes to the speaker. There's actually a switch on the speaker, so this has to be plugged in to switch it on. Take our speaker here. Boy, this thing looks dirty because it's got that. That's the other thing that really sucks about these is there's the rubber stuff. It's got that rubber coating that turns into a sticky coating over the years. So yeah, I don't know if I'd recommend you going out and buying these, but if you got a pair, or you want to use this hack for other audio gear, it's good. All right, everything's plugged in. There's also no standby light. Yeah, I'm not a fan of that either. But anyway, I'm going to turn things on. It turns green. And you'll notice I can turn this. You'll hear that hum. And that hum is super annoying. And that was, by the way, the reason it's doing that is because I have it actually going to a non-terminated source. But it's a way to give you an example. It's actually going to an audio input, so the input is going to an input, so it's not a terminated source, it's not properly terminated. But if I remove the USB cable, you can see it gives you an idea of how that works. Now, fortunately, I have a proper ground source with my phone here. And the phone, don't use a phone for your initial testing. I did this off camera with other equipment first, because you don't want to break your phone, especially if you're testing ground currents like this. But if you already, if you've already tested it safely and you know it's good, then you can move up to your more expensive devices at your own risk. And so I'm going to go here and play you something from the Cotton soundtrack, which is already online. Woohoo! The Cotton Reboot soundtrack. And you'll see right now the audio is just plugged in with regular audio. What I'm going to do is I'm going to plug in the USB, and we'll see if the ground hum shows up. All right, sounds nice. Now let's plug in our USB. And there's no ground hum. I'm going to go ahead and turn this way up. Actually, it's already max volume. It's a little tiny bit. But that might just be speaker, like general amplifier hum. I mean, this is real loud. So if I crank this way up, not bad. And that'll be louder than I'll play it anyway. And if I pause it, the hum is very, 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 very minimal now. You can hear it actually. So if you're close, you can hear it, but it's super minimal. So here's without the USB. I'm going to crank it all the way up. This is without the USB. With the USB. So this is with the USB, without the USB, with the USB, without. So yeah, there still is a little bit of hum probably from that leakage current, but we're talking, boy, way quieter than it used to be. Probably went down 12 decibels or more. So yeah, I'm pretty happy with that. I count that as a success. And success, like Cotton. The Cotton developer. One thing that is a disadvantage to doing this that you should all know about, just to give full disclosure, is there will be a voltage drop across those diodes. There always is a voltage drop across diodes. And if it's a nice Schottky diode, it should be around 0.3 volts, but it can be as high as 0.7, even 1 volt, I think some of them might do. So that's pretty uncommon. And that voltage will drop more as the current increases. So at your louder volumes, you will have a higher voltage drop. But if we measure here, what are we getting in our DC voltage here? 19.04 volts, so 19 volts basically. And if we measure the incoming, we're getting 19.13. So those are decent Schottky diodes. It's like a 0.15 voltage drop. But let's go ahead and actually play our music again and see at full volume, at least for, I'm only using one channel right now, so half, let's say half the maximum volume, because my other speaker is still in the cabinet, what the actual voltage drop will be. Let's wait for it to load the next song. It's actually a good way to test it too. So 19 volts. So with the max volume, I was getting about 18.4 on the output from the bridge rectifier and getting around 18.3 on the output from the diodes. So that's incredibly good. 100 millivolt drop is almost totally negligible. The one thing I am concerned about, though, is that this originally is a 20 volt system. This capacitor probably could still use replacing. I'm sure it's in not great shape because I think what it might be doing is struggling to deliver that load. However, using a transformer, you always get some voltage drop anyway, so it's hard to say which one of those issues it is. I'll order a capacitor just to be on the safe side. They're only a few bucks, under $5 or whatever, and you know, put it in later if I feel like it. But for right now, it's going really well. And when I get more time, I'll put in that capacitor and a power fuse. So yeah, you can hear it. It sounds really good. There's no more hum. I'm going to go ahead and show you on camera. We've got the speaker at max volume. Oh, dropping the lamp here. Just one last test to show you all. Speakers at max volume, and I'm going to go ahead and plug in the USB. And yeah, you can't, I mean, I can't hear the hum. So yeah, that's it. Again, the recap. If you have ground hum in your speakers with your amplified power system, it's a result of current sharing between the AC, it's current feeding back and then being transferred along your AC line. And the way that typical power supplies handle that is they use switching power supplies, which have an optocoupler, which uses optics to isolate it. But since this uses a old school transformer, class 1 power supply, it doesn't have that. The ways you can solve that are: 1, you can actually run it from a different circuit in your house, maybe run an extension cable from a different room. 2, you can use a very large, bulky isolation transformer, which are quite expensive but very nice to have around, and they're heavy. 3, you can do an improvement usually by changing out the offending capacitor, because usually this problem will be exacerbated by an aging capacitor, the bulk capacitor as they're called, on the output of your bridge rectifier stage. And 4, the other way you can fix it, which I have done here, which is perhaps the easiest way and most cost effective, is you simply isolate the output capacitor, or your output source, from your output of your bridge rectifier. Your output, you basically isolate your DC output. In this case, actually, I might even get better results with that voltage drop by isolating after the capacitor. It's probably what I should have done, actually, now that I think about it. So yeah, this was just the easiest way to do it. But yeah, because ideally the capacitor would share current more directly with the bridge rectifier stage, because they kind of work together. But yeah, you just put some diodes after your capacitor going to your circuit. You do one ground wire, or one for ground in reverse, cathode anode in reverse, one for positive, because that's how diodes work. They're directional with current. And yeah, that's it. Disadvantages, again, you'll have a little bit of voltage droop across the diodes, because that's how diodes work. And you will have a tiny bit of leakage current. It's usually totally negligible. And of course, the time it takes, and the parts and whatever. But it's a nice, easy way, I think, to fix hum problems, and I recommend doing it. If you liked this video, do not subscribe. I don't care if you subscribe. I mean, you can if you want. What I am more interested in is hearing from you. So feel free to leave a comment. Tell me if this video helped you. I love hearing when people say, like, hey, that fixed my problem. Thanks for sharing. Because that's what a lot of videos have helped me with. I've learned a lot online, and I'm just trying to pay it forward. So when I hear from folks that help me, then that makes me happy that I'm sort of giving back to the electronics community as a whole. That's it for this video. This is Sega Sonic Fan, signing out.